Hello everyone. The title of this video is Solve Absolute Value Inequalities with is greater than, right? See the greater than in quotes. So these inequalities, you're going to have the absolute value of some expression is greater than some number or is greater than or equal to some number. Right? I just didn't type in the is greater than or equal to as well, just to keep the title of the video shorter. Alright. So all the exercises I'm going to do in this video, all the examples I'm going to show you, are going to be taken straight from a free online textbook from openstacks.org, and that textbook is their Intermediate Algebra 2nd edition. And these exercises are taken from that book's section 2.7, Solve Absolute Value Inequalities, and it's the section here titled, Solve Absolute Value Inequalities with, quote, greater than, or is greater than or equal to. And in each exercise, we're asked to, solve the inequality, graph the solution on a number line, right, that's understood, and write the solution in interval notation. Alright, so example 1 is going to correspond to exercise 468, and I'm going up to example 12. Right, example 12 will correspond to exercise 479. And if you'd like to skip around, if you'd like to say, hey, I'd like to see number 473, that would be example 6. You can go to the description for the video and click on the timestamp for example 6. I've got timestamps for all the examples to make navigating through the video a little easier, hopefully. Alright, so let's begin. So again, I'm going to solve each inequality, graph the solutions on a number line, write the solutions in interval notation. Alright, so before I get into example 1, I'd like to talk a little bit about absolute value. Now, I'm hoping that you've seen my video on solving absolute value inequalities with the less than, is less than or is less than or equal to, and also that you've seen some examples from my video on solving absolute value equations, because in both of those I discuss a little bit about how to interpret the absolute value of something, which I'll do again here real quickly. Okay, so the absolute value. Right, the absolute value of a number. One way it can be interpreted is the distance of that number from 0 on the number line. Right, distance from 0 on the number line. Right, so for example, where the absolute value of 5 is 5, right, because 5 is 5 units away from 0. The absolute value of -5 is also 5, right, because it's still 5 units away from 0. So absolute value is never negative. Right? It's not negative, ever. Or non-negative. So keep that in mind as we go through our examples here. Right. Now when solving an absolute value equation or absolute value inequality, again, you may have noticed this in my previous videos, I'm going to perform some algebra steps, right, adding, subtracting, multiplying, dividing, in order to get the absolute value expression all by itself. And I've been doing it so that it's all by itself on the left side of the equal sign or the inequality symbol. So I'm going to say do what you can, whatever legitimate algebra moves you can make to get the absolute value symbol right, the absolute value expression, that's an R in there, sorry, expression alone on one side. Now I'll say on the left side just to stay consistent with the way I've been doing the other videos. And you can do it on the right side if you wish, but I'm doing it on the left side, so when we read it, we'll see something like this. We'll see the absolute value of some expression, which in this intermediate algebra textbook, from OpenStax, they're representing an expression by the letter U. So I'll have this, the absolute value of some expression, some number U, is greater than, right, all the inequalities in this video will have is greater than or is greater than or equal to. Right. And then some number which will be represented by the lowercase a in this textbook. Now, in order for this to actually have some meaning, this number here on the, once you have isolated the absolute value expression, the number on the other side, in order for the inequality to be interesting, right, for you to actually need to do something to solve it, this has to be a positive number. All right, and I'll talk about, well, what happens if this number on the other side is not positive? What if it's 0 or negative? What do we do then? I'll talk about that in a little bit. But if that's a positive number, and I'm saying, the absolute value of U is more than A, and if you think of absolute value as distance from 0 on the number line, right, say here's a number line, here's 0, and what numbers have an absolute value of A? Well, that would be A, right, A being positive, so to the right of 0. That is A units from 0, right, has an absolute value of A. But so does the opposite of A, right? That's also A units from 0. So when we're talking about, hey, what numbers could this U represent? We're looking for numbers that have an absolute value bigger than A, that's farther than A units from 0. So all these numbers over here, right, to the right of A, these numbers are farther than A units from 0. They have an absolute value greater than A. So U could be one of these numbers, but not A itself, right? So an open point or parentheses on that, because that would have an, A has an absolute value equal to A, not greater than A. This is strictly greater than. So U could be one of these numbers to the right of A, but also, it could also be one of these numbers to the left of the opposite of A, but, not the opposite of A itself. So from this picture, we can establish an equivalent compound inequality to our absolute value inequality. So when I see the absolute value of some expression is greater than a positive number, I'm going to rewrite this as this equivalent compound inequality. Right? This statement here is equivalent to saying that U, right, the number U is less than or equal, less than negative A, right, to the left of negative A, or, right, because there's separation here, right, and one or the other. It could be these numbers or these numbers, but it can't be both, right? You can't be both, so it's not and, it's got to be or. Or U could be a number greater than A. And either way, U is some number with an absolute value more than A. Alright, so this is going to be key here. So I'm going to isolate the absolute value on the left, get absolute value of some expression is greater than, and then hopefully, again, some positive number. And once I had this, I'll then write the equivalent expression, the equivalent compound inequality, this OR inequality, right? In order for this statement to be true, u is either to the left of negative a, right, or u is to the right of positive a. One of those has to be true in order for this absolute value inequality statement to be true. And then I would solve these and graph the solutions and draw, the solutions in interval notation and all that. All right? But this is key, right? Writing this equivalent compound OR inequality without absolute value symbols, right? Making the absolute values disappear. All right, so first I'll start with this example. All right, this is already set up the way I wish, where I have the absolute value expression all by itself on the left side. All right, absolute value of x is greater than 3. So it's already set up the way I wish. All right, absolute value greater than some positive number. Oh, and yeah, by the way, if this were greater than or equal to, well, then these would be included, and you'd have the or equal to, underneath each of these inequalities here. That's the only thing that would, you just add the or equal to all the inequality symbols. Simple enough. All right, so the absolute value of x is greater than 3. This is equivalent to saying that, well, x must be greater than 3, right? That's either x is to the right of 3, or x is a number less than negative 3. Right? You're to the right of 3, or you're less than negative 3. Right? Kind of like my picture here with the u's and the a's. And then you solve this. Now both inequalities here are already solved for, right? The variable's already alone, so here they are. There's a description of the solutions of this absolute value inequality. I could replace x with any number greater than 3, and this would be true. Right? And try it out, test it out. Plug in 4 for x. Right? You'd have absolute value of 4, which is 4. Is 4 greater than 3? Yes. How about 5? 5 would work. It would make 5 greater than 3, yeah. Plug in 6, 7, 8, a billion, 3.5. Right? Anything greater than 3 would make this statement true, the original statement. But also, right, or x could be replaced with any number less than negative 3. So negative 4, right, left of negative 3, negative 4, negative 5, negative 6. Go ahead and test that out. Plug in negative 4. Right? The absolute value of negative 4 is positive 4, and 4 is greater than 3. That's true. And that'll work for any number less than negative 3. Right, but not 3 itself, not negative 3 itself, right? Because those have absolute values equal to 3, not greater than 3. So 3 and negative 3 are not included. All right, and then we make a graph. All right, graph these solutions on a number line. Now, hopefully you recall how to graph an OR inequality, right? A compound inequality with the word OR. Basically, you just put both graphs up. Here's negative 3, right? Here's positive 3. The numbers that are mentioned in the solutions here, and we have all the numbers to the right of 3 are solutions, but not 3 itself, so I put parentheses on 3 or an open point. Or all the numbers to the left of negative 3 would be solutions, right? All the numbers less than negative 3, but not negative 3 itself, right? So again, a parentheses or an open point on negative 3, and there you go. Right? There's a picture of all the solutions on a number line. Right. And again, test it out. Pick a number bigger than 3, plug it in. It should make it true. Pick a number less than negative 3, plug it into the original statement, should make it true. Additionally, you can also see what makes it false. Right? Any number between negative 3 and positive 3 would not make this true. Right, like 0. If x were 0, is the absolute value of 0 greater than 3? No, it's not. Right? 0 is not greater than 3, and that would be the case for any number between negative 3 and positive 3. That's why they're not on the graph. All right, and then interval notation for this set of solutions. Now again, I'm hoping you've seen a previous video on graphing and compound inequalities with the word or. You see how this picture of solutions is broken up into two pieces, right? There's a break in it, a gap. So you need to write an interval for each piece, and then use the union symbol to represent the gap, or the word or. Right? And you always go from left to right, low to high, when you're writing interval notation. So this first piece of the picture, going from left to right, that's going from negative infinity, right, all the way to the left forever, up until negative 3. And then parentheses always on infinities, right, because infinity is not a number. And we said negative 3, right, is not a solution. So I indicate that with, again, a parentheses on negative 3. So there's the interval for that piece of the picture. And then I have the symbol for the word or, which is this U. Right? Remember, this is the union symbol, kind of is the set notation symbol representing the word or. And then for the second interval, right, going left to right, goes from 3 to positive infinity. And again, parentheses on the 3 because it's not a solution, and parentheses on the infinity because, infinity is not a number. And there you go. This should be considered, this whole thing, right, both intervals connected by the union for the gap, right, telling me there's a gap there. This is the interval notation for this set of solutions, right? All the numbers less than negative 3 work. All the numbers greater than 3 work. All right. Now, this was an example that I wanted, right? With absolute value on the left, positive number on the right. What if that number isn't positive, though? All right, I'll show you. Now, this is not from the textbook. This is just another example I'm making up here, just to show you what happens. Well, what if? So, separate example. What if I had the absolute value of x all by itself on the left is greater than or equal to, I'll do greater than or equal to in a second, is greater than 0. That is not positive. All right, that is not positive. Well, if this is the case, remember that the absolute value of a number is non-negative. Right, or not negative. So every number I plug in is going to give me a number over here that's greater than 0, except for 0 itself. So I can still do that setup where, in order for this to be true, x would have to be greater than 0, right? Or x would have to be less than the opposite of 0, but the opposite of 0 is still 0. So really, what you're seeing here is the solutions to something like this, here's 0, is every number except 0. Right? All the numbers greater than 0 would work. All the numbers less than 0 would work. The only number, that's why I've got a hole here above 0, the only number that wouldn't work here is 0 itself. Right? 0 is not greater than 0. 0 is equal to 0. So every number is a solution except x equals 0. All right, so there's a description of the solutions here, a graph, the interval notation. You go from negative infinity to 0, parentheses, union. Again, there's a gap here. Technically, that's a hole, a break in the graph. And then parentheses, 0 to infinity. Right, this would be the interval notation for something like that. Now, what if I had greater than or equal to? And what if I have the absolute value of x is greater than or equal to 0? All right, well now 0 is a solution, right? You had the greater than part, which had everything was a solution except 0. As soon as I throw in the equal to part, 0 is a solution. So for something like this, where the absolute value of a number is greater than or equal to 0, this will always happen. This is always true, no matter what you plug in for x. So that tells me that x can be any real number, positive, negative, or 0. All right, so you could write this, or all real numbers are solutions. The graph, right? The graph would just have all the numbers. Right? Just mark off every single number from the far left to the far right forever is a solution. The interval, right? Now this doesn't have any breaks in it, no gaps, so it's just one big interval. Going from left to right would be from negative infinity on the left up to positive infinity on the right, and you always put parentheses on the infinities, and there would be the interval notation for such a thing. Okay, so now those are the cases when the number on the other side is 0, right, not positive. What if the other side has a negative number? How about the absolute value of something is greater than, I don't know, -1? Now this one's even easier. Now there's a negative number on the other side when you isolate the absolute value. Well, remember, the absolute value of a number is never negative, right? It's not negative. And something that's not negative will always be greater, or greater than or equal to, but will always be greater than something that's negative, right? So something like this, where if you isolate the absolute value, and then you have the absolute value of something is greater than or equal to a negative number, just like the previous example, this always happens. So same deal here. This would have all real numbers as solutions. X can be any real number. And then the graph and interval notation would be these here. Right, same as the previous example when it was greater, absolute value was greater than or equal to 0. So the only one that's even kind of tricky here is when you have the absolute value of something just greater than 0. If that's the case, every number will be a solution except for 1. All right, every number will be a solution except for 1. You may or may not come across that scenario in whatever exercises you're working on. Okay, so now finally to the second example. All right, where again I'm using this concept here. We're going to get the absolute value alone is greater than or equal to, and then hopefully some positive number. Because remember, if it's 0 over here, or if it's negative, that's like one of the scenarios I just talked about on the previous page. Once we have this, we're going to write the equivalent compound inequality with the word or, and then solve these and state the solutions, make a graph, and put things in interval notation. All right. So this example 2 is pretty much like example 1, but instead of 3 you have 6. Right? So the absolute value of x is greater than 6. Well, the equivalent compound inequality, right? This will be true if x is greater than 6, right, to the right of 6, or if x were less than -6, right? If x were some number to the right of 6, this would be true. Or if x were some number to the left of -6, you'd have numbers that were had, you know, further than 6 units from 0, that would also be true then. And both of these are already solved for. All right, the variable's already alone, so done with that. There's a description of the solutions. And, you know, I leave it to you to test them. Pick any number greater than 6. 6.1, 7, 8. Plug it into the original inequality and see that it's true. Or, you know, take any number less than -6. You know, -6.2, -7, -8, -9. Plug it in for x and you'll see, oh, that's true as well. So here's a description of the solutions. All right, then the graph, again, pretty easy. You know, the numbers mentioned in these solutions are -6 and +6. And according to this, all the solutions are the numbers greater than 6, you know, but not 6 itself, so I put parentheses on that. Or the numbers less than -6, right? So over here, but not -6 itself, right? So here's the graph, and then the interval notation. Again, there are two separate pieces. So I need two intervals, and then I'm going to connect them with the word or the union symbol. First piece goes from -infinity up to -6, but, you know, not including -6, so I got parentheses. In union with, right, representing where the gap is, or, and then 6 to infinity. Right, going from left to right, and then parentheses on both of those as well. And there's the interval notation for the set of solutions. Okay. So far, pretty similar stuff. This is also pretty similar. The only difference for example 3 is that instead of is greater than, it's, you know, is greater than or equal to. All right, so yet again, the absolute value symbols alone is greater than or equal to, you know, some positive number. So I'm going to take this and write, you know, an equivalent compound inequality, right? One of these OR inequalities. The only way this would be true is if x were, you know, greater than or equal to 2, right, to the right of 2, or if x were less than or equal to -2. Right, if x were to the left of -2, we'd have numbers with an absolute value greater than 2. And -2 would also work because, you know, that has an absolute value equal to 2, satisfies the equal part. And both of these are already solved for, right, the variables alone. And again, you can test it out, right, but here are the solutions of the inequality. All the numbers 2 or greater, right, so go ahead, plug in 2, plug in 3, 5, a billion, right? It'll make the original statement true. Or all the numbers less than or equal to -2, right? So plug in -2, -3, -4, -1,000, right? And it'll make this true, and I leave that to you to test that out. All right, then the graph on the number line, again, the numbers mentioned here are -2 and +2 in the solutions. And the solutions are all the numbers, you know, greater than or equal to 2. So now 2 is included, so I'm going to put a rectangular bracket or a closed point above that. Or, right, all the numbers less than or equal to -2. So bracket on -2, right? There's a picture, a graph, right, of the solutions. And then the interval notation, yet again, there's a break, there's a gap, right? So we're going to represent that gap with the union symbol, and let's go one piece at a time here. First piece, left to right, going from -infinity up to -2. Always parentheses on the infinities, and then -2 is a solution. Right, so I got a bracket on that, rectangular bracket. Gap, right, so union, right, for the word or, and then from 2 to +infinity, bracket on 2, parentheses on infinity, right, and there's the interval notation for our solution set. Okay, next example is pretty much the same as 3, but 2 is replaced by 5. So not much changes here, right? The absolute value is isolated, got greater than or equal to, and then some positive number. So if that's the case, right, the equivalent compound inequality, you know, the only way this is true is if x is greater than or equal to 5. So basically I just write a version where the absolute value symbols are gone, and then just flip the inequality and be on the left side of the opposite, right? X is less than or equal to -5. And yet again, this is already solved for, right? The variable is alone on one side of both of these inequalities. So there's a description of all the solutions, right? And you can, again, test it out for yourself. Replace x with 5 or any number greater than 5 in the original inequality and see that it is a true statement. Or, replace x with any number less than -5, -5.2, -6, -8, whatever. Or equal to -5, and you'll see that you get a true statement again back in the original inequality. And the graph, right, here's a number line. The numbers mentioned in the solutions are -5 and +5. And we have all the numbers greater than or equal to 5 are solutions, so to the right of 5 and including 5. Or all the numbers less than or equal to -5 are also solutions, right? So to the left of 5 and including -5. So there's the graph. And then yet again we have another picture where there's a break in it. So when I draw interval notation here, I'm going to have two intervals with the union symbol in between them. First interval here is -infinity up to -5, right? Including -5, so a bracket on that. In union with, and then from 5 to +infinity. So there's an interval notation describing the solutions of this inequality, right? The numbers I can replace x with and make the original statement true. Okay, so for the first 4 examples, the absolute value expression was just the absolute value of a single letter, a single variable. From here on out, the rest of the examples, it's not just the absolute value of a single letter. We have the absolute value of a little more complicated expression, like here it's 3x minus 8 instead of just x. But it's no different than, that 3x minus 8 is like the u, right? They represent any expression here with the variable u. So 3x minus 8 here is like the u from the first page of the video. Okay, so I've got the absolute values already alone. I don't need to do any adding, subtracting, multiplying, dividing, right? The absolute value expression is already on the left by itself. I have is greater than, and then, a negative number on the right side. Remember, if the number on the right side is negative, we really don't have to do any work. Because look, the number on the right side is negative. The left side is the absolute value of something, so that's not negative. And something that is not negative will always be greater than something that is negative. So this, again, like you saw in one of the examples I put up earlier, this will always be true, no matter what I put in for x. The left side will always be greater than -1. So that tells me that, again, the variable here is x. X can be any real number. Or you can just write all real numbers or something. Then the graph, right, the picture of the solutions, I mean, just indicate that everything is a solution, from the far right forever to the far left forever. So let's draw an arrow, a left to right arrow, the whole number line. There's the graph. And then this is just one big piece, right? There's no breaks in it, no gaps. So one big interval from far left to far right here is -infinity, comma, to +infinity. And always parentheses on the infinities. Right? So there's the interval notation for the entire real number line. Go ahead and try it out. Pick any number you want and replace x with it. And the left side will be greater than -1 after you take the absolute value and everything. It'll always be true. All right, so yeah, if you isolate the absolute value and you have is greater than a negative, it's easy. All real numbers will work. Don't have to do anything more than that. So number 6, example 6 here is exactly the same then. See, I have the absolute value alone already, right? And that's, again, that's going to be something that's not negative no matter what I plug in for x. Non-negative is, something 0 or greater. And then this side is negative. -2. And as I said with example 5, something that is not negative will always be greater than something that is negative. So just as the last example, this is always true, always happening. So just as the last example, x can be replaced by any real number. X can be any real number. And then the graph, right, again, here's a number line, just indicate that every number is a solution no matter what you pick for x. This is a true statement. And the interval for the entire real number line is that -infinity to infinity, right, with parentheses on the ends. Right? Yeah, so again, pretty easy example there, just like 5. All right, so number 7, all right, example 7 gets a little more interesting. Because we have what we want, right? The absolute value is alone, right? I don't need to do anything to get it alone, it's already alone, is greater than, and now there's a positive number over here, much more interesting. And now I can go back to that first page, right, and write the equivalent compound inequality. Right? So this is equivalent to, this is only going to be true if the number inside, right, the number inside the absolute value symbols, if 3x minus 2 is greater than 4, right, say 5, 6, 7, 8, whatever, this would be true. Or if this expression inside, the number inside, 3x minus 2 is less than -4, right? So this expression is either to the right of 4 or to the left of -4. Now, this is not solved for, right? We have to get the variable alone in both of these. So I'm assuming you know how to do that. So for this one, I would, add 2, divide by 3, have x is greater than 2. All right, you'd have 6 divided by 3 is 2. And I didn't multiply or divide by a negative number at any point, so the inequality doesn't flip. Or, same thing over here, I would add 2, giving me -2 over there, then divide by 3, giving me -2/3 over there. And now they're solved for. Here's a description of the solutions. All right. So the solutions, what can I replace x with to make this a true statement? I can replace x with any number greater than 2, or I could replace x with any number less than -2/3. And test this out. Pick any number greater than 2. Right, I'm just going to do one. Say 3. 3, right? 3 times 3 is 9. 9 minus 2 is 7. The absolute value of 7 is 7. Is 7 greater than 4? Absolutely it is. And you could try that with any number greater than 2, and it should work. Try these other numbers, right? Or, take a number less than -2/3. Well, how about -1? 3 times -1 is -3. -3 minus 2 is -5. The absolute value of -5 is +5, and is 5 greater than 4? Absolutely. And you could do this with any number less than -2/3, and it should make that true. So here's a description of the solutions. and I'll graph these on a number line, right? The numbers mentioned here are -2/3 and positive 2. So and again, make sure you're putting numbers in the correct place. You know, negative 2/3 should be to the left of positive 2. And our solutions are all the numbers to the right of positive 2, but you know, not 2 itself. So parentheses or an open point there. Or all the numbers less than negative 2/3, right, to the left of negative 2/3, but not negative 2/3 itself. And there's your graph of the solutions. And then the interval notation, you got the two separate pieces again, so you need a union symbol kind of to represent the gap. We got the first piece is from negative infinity up to negative 2/3, parentheses on both, because you know, not solutions, negative 2/3 not a solution, in union with, and then the second interval here is from 2 to positive infinity, parentheses on both, right? And there's the interval notation for the set of solutions. Okay, moving right along. Example 8, pretty similar to example 7. Now you may have noticed that so far in every single one of these the absolute value is already by itself, right? If I had the absolute value of x plus 3 minus 5 is greater than 2 or something, I would have to add the 5, right, to get the absolute value alone. Okay, so just keep that in mind. That, you know, just because every single example in this particular textbook has the absolute value alone on the left already, doesn't mean you'll always see that in, you know, other textbooks. So just be aware of that. Right? You may have to do something to get the absolute value alone, but here we don't. Right? The absolute value of 2x minus 1 is already alone on the left side. It is greater than, and then again, some positive number, positive 5 on the right. So this is actually something I can apply the rule from the first page to. All right, this is actually interesting. So this absolute value inequality is equivalent to saying that, you know, 2x minus 1, right, the number inside the absolute value symbols, it has to be a number either greater than 5 or 2x minus 1, right, the number inside the absolute value symbols, has to be some number less than negative 5, right? It's either something to the right of 5 or it's something to the left of negative 5, right, to have an absolute value greater than 5. Okay, now these are not solved, right, so I solve them. First one, I would add 1, divide by 2. We have x is greater than 3. Or, in this one, same thing. I would add 1, you know, get negative 4 over here, divide by 2, get negative 2. X is less than negative 2. And here are the solutions. We have solved for the variable in both those inequalities. And again, try it out, test it out. The numbers that I can replace x with to make this absolute value inequality a true statement are, you know, I can replace x with any number greater than 3. Right, so 3.4, 4, 5, 6, but, you know, not 3 itself. Or I could also replace x with any number less than negative 2, and it would make this true. And again, I leave it to you to test some of those out if you want. All right, then the number line, or the numbers mentioned here, are negative 2 and positive 3. And all the numbers, you know, greater than 3 are solutions, but not 3 itself. All the numbers less than negative 2 are solutions, but not negative 2 itself. And there's the graph. And then interval notation, again, you have the two separate intervals, you know, with a gap between them. So that'll be like represented by the union symbol. So we have from negative infinity to negative 2 for this first interval, parentheses on the negative 2 because it's not a solution, in union with, and then the second interval, we're going from 3 to positive infinity as you go from left to right, and parentheses on the 3 because again it's not a solution, and always parentheses on the infinities. Right? There's the interval notation for this set of solutions. Okay, number 9 is pretty similar to number 8. You have the absolute value alone, right? The only major difference is that it's greater than or equal to instead of it's just greater than. So I got absolute value alone on the left, as we like, is greater than or equal to, and then again some positive number, which makes it interesting. I can use that rule from the first page. Say this is equivalent to the following. The number x plus 3, that number has to be either greater than or equal to 5 in order for this to be true, or this x plus 3 in the absolute value symbols there could be less than or equal to -5, right? Either to the right of 5 or to the left of -5, right? That way the absolute value is greater than 5. And it could be equal to 5 or equal -5 to have the absolute value be equal to 5. And then I solve both of these. Subtract 3, we get x is greater than or equal to 2. Or here subtracting 3, x is less than or equal to -8. And there's a description of the solutions. So the numbers I can replace x with in this to make it true, I can replace x with 2 or greater, or I could replace x with -8 or less. And the original statement will be a true statement. Graph, right here, number line, the numbers mentioned in the solutions here are -8 and +2. The numbers greater than or equal to 2 are solutions, so 2 to the right of 2 and equal to 2, so I got a bracket on 2 or a close point to indicate that 2 is a solution. All the numbers less than -8, including -8, right? And bracket on -8, those are solutions as well. There's the graph, and then the interval notation, the first interval here from -infinity up to -8, parentheses on infinities there, and bracket on -8 because it is a solution. Then union for the gap here that represents the word or. And then the second interval is going from 2 to infinity, bracket on 2, parentheses on infinity. There's an interval notation for your set of solutions. Okay. Example 10, I'm down to the last 3 here, last page. Example 10, again, pretty similar setup to the previous 2 examples. You got the absolute value expression already alone, which is great. Absolute value of x minus 7 is greater than or equal to, and then a positive number, which is wonderful. So now I can write that equivalent compound inequality. This will be true when x minus 7 is greater than or equal to 1, or whenever x minus 7 is less than or equal to -1. Right? When x minus 7 is to the right of 1 or to the left of -1, this will be a true statement, or equal to -1 and 1. Solving each of these, I would add 7. We get x is greater than or equal to 8, or adding 7 to both sides of this, x is less than or equal to 6. And there you have it. Those are the solutions of this inequality. And again, I leave it to you to test it out. Try some numbers out. In this inequality, I could replace x with any number that's greater than or equal to 8. Right? So like 8, 8.5, 9, 10, whatever, and this would be a true statement. Or I could replace x with any number less than or equal to 6. So 6, 5.5, 5, 4, 3, 2, 1, any negative number, and plug it in here, and this will be a true statement. And then for the graph, right, the numbers mentioned in the solutions are 6 and 8. Numbers greater than or equal to 8 are solutions, indicated with that picture. Numbers less than or equal to 6 are solutions, right, indicated with that picture in the bracket above 6. And then interval, right, the left interval there's from -infinity up to 6, bracket on 6. Union, then second interval from 8 to infinity, bracket on the 8. And there's your graph and interval notation for that set of solutions to this inequality. Right. Now finally, right, these last 2 examples, finally the absolute value is not alone. So we have to do some stuff, right? So for number 11, you see how the absolute value of x, right, the absolute value expression is not alone. So I would like to get it alone. Isolate it, right? Now in order to do this, it's going to take away the 4 from both sides. Alright, that'll give me 3 times the absolute value of x is greater than or equal to negative 3. And then to fully isolate the absolute value, right, it's being multiplied by 3 right now, so I need to divide both sides by positive 3. Now, dividing by a positive will not change the symbol. Right? Will not flip the symbol. So I have the absolute value of x is greater than or equal to still, and then negative 1. Right? So I've isolated the absolute value. I got the absolute value alone on the left there. Is greater than or equal, oh look, a negative number on the right side. And so this is like some examples from earlier in the video. The left side is not negative, right? Absolute value is not negative. And something that's not negative will always be greater than or equal to something that's negative. In fact, it'll always be greater than something that's negative. So just as before, when you have the absolute value alone on one side is greater than some negative, this is always true, no matter what you pick for x. So x, the variable here, can be any number you want. Right? X can be any real number. So there's a description of the solutions. Then the number line, right, remember how we saw this earlier, just indicate that every number is a solution. Just the whole number line again, basically. Then this interval notation would be from negative infinity to positive infinity with parentheses on them. There's the graph and interval notation. Alright, so yeah, the only major difference between this one and ones earlier is that you had to perform some steps to get the absolute value alone. And the same thing goes for number 12 here. Alright, example 12, I want to get this absolute value of x alone. So I would subtract 6, giving me negative 5 over here, and then divide by 5, giving me negative 1. So I have absolute value of x is again greater than or equal to negative 1. And it's the same, basically it's the same exact inequality. This is always true. The absolute value of something is always greater than a negative. So this has every real number as a solution. And you can test it out. Pick any number you want, plug it in for x, and the inequality will be a true statement. Alright, and it has this graph and this interval notation. Alright, so again, most of these examples had the absolute value alone already. Just be aware that if you're looking in other textbooks or other homework programs, whatever, you're going to come across problems where you'll have to do some steps. You'll have to do some algebraic manipulation yourself to get the absolute value alone. So just be aware of that. Be aware that you might have to do that. Alright, so hopefully watching me go over these several examples where you have the absolute value of some expression is greater than or equal to some number. Hopefully watching me go over these examples will help you when you're working on similar problems. And thank you very much for watching.